And I'm so sorry that we were going to take a picture, and we are going to discuss a little bit on the topic you have on the screen. Actually, my presentation is going to be a very simple one. It's going to be actually more philosophical, not many equations, but about a topic that is somehow scattered in the literature, is covered, is like hidden in some remarks, and it's still an important point that deserves some reflection. So we are going to reflect on this fact, and I hope you will like it. So actually, as I said, it's going to be quite philosophical. So I'm going to say some philosophical thoughts about geometric mechanics or geometric field theories. And I begin with, the pointer is this one, I think. Here we are. About symmetry. So it can be either in the Hamiltonian or the Lagrangian formulation of systems. And symmetry, that means a group acting on a system such that the Lagrangian or the Hamiltonian or the elements working there are symmetric with respect, are invariant with respect to the group, induce interesting objects. One of the first one is reduction, right? Reduction is like a gold word in geometric mechanics, and with this procedure, what you get is a smaller configuration space. So you use reduction, so you make the configuration or phase space smaller. So that's idea number one. But symmetry, M in ether, we know that also provides conserved quantities. And there are different objects. So reduction is elimination of variables, and Nether theorem is a conservation law. So there are main ideas in geometric mechanics. I mean, symmetry is also found in many other objects. I don't know, solutions, stability, blah, 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 blah. But actually, these other points are always somehow connected with the first two ones, right? Okay. So my goal, my philosophical goal, is to build a connection, not a connection as a geometric object, but a connection as a philosophical word between these two things, right? Which is in the literature hidden, and I'm going to try to put it as clear as possible. So the main characters of my play are going to be functions from a manifold to another manifold. So we are looking for maps from N to Q satisfying some equations, right? For example, you can thought of these maps as sections of this trivial bundle, right? So that's a way, okay? It's a waste of time. Think of this instead of thinking of S as a section of this bundle. But there are many other situations where the interesting objects are sections of bundles, right? So actually, even though I'm going to work with these for the sake of simplicity, everything can be done here. So if you're interested in sections of bundles, you can use all the philosophical remarks I'm going to put here. And this setting actually is the setting where everything today fits in. For example, mechanics. Mechanics is a trivial bundle where n is time, is the real line. So it's a section of this bundle is a map from the time variable to a manifold. That's mechanics. But also can be, for example, a vector field in fluids. A vector field is a section of a bundle, the tangent bundle. Or it can be connections. A connection is a section of a bundle, the bundle of connections. Or it can be a metric in relativity. That's a section of a bundle of metrics, right? So many, actually all possible interesting situations I know are sections of a bundle. But okay, let's go to this situation. Okay, I said that my philosophical remarks were going to be okay for Hamiltonian and Lagrangian, but I'm going to be in the Lagrangian side, right? And then if you want to complete the computations for the Hamiltonian side, okay, go ahead. So that means that we have a Lagrangian function. So first order can be done in higher order, but okay, let's be in the simple case. So that means that the Lagrangian function is defined or depends on first derivatives. Those are elements on the jet space, and if the bundle is trivial, or this is like one forms in n taking values in TQ, right? For example, if n is the real line, we have classical mechanics. Actually, this, I mean, T star of R is nothing, and the tensor product is nothing. This is just time-dependent mechanics. This is R standard T, TQ. But if the base manifold is bigger, then we have field theories, relativity, Young-Mills, electromagnetism. We have many other things, right? Or if we have bundles, then we have the one jet bundle of local sections. That's an affine bundle over Y, and you can continue the computations. But again, I'm going to be here, right? We have the Lagrangian. And now symmetry. Symmetry is a Lie group acting on Q, and I'm going to consider nice actions. So the action is free and proper. Otherwise, you have singularities, and nowadays there is not a theory of singular Lagrangian reduction. That's an open problem, by the way. So there is a lot of done in Hamiltonian singular reduction. Lagrangian singular reduction is an open problem. So I'm going to consider good actions, so I don't have singularities. And we assume that the Lagrangian is invariant. Then we have a drop Lagrangian. The Lagrangian is invariant under the action of a group, so it goes to the quotient. This is a small L, right? But the problem is that this manifold, this jet space over G, I mean, what is that? Okay, there is a trick, a fiber bundle trick, which works with principal connections. I mean, the action, the proper and free action of G on Q induces a principal bundle. This is a G principal bundle, right? So you consider principal connection omega here, any principal connection, right? So there is an identification. Actually, this identification looks like a bit nasty, because there is this T star n, but you can drop it because the action of G doesn't affect the T star n. So the main quotient is on TQ. So we have TQ over G, and then it drops to T of the quotient, sigma, plus this is the adjoint bundle, right? So this is a very classical object in reduction, this Euler Lagrange-Poincare reduction, right? So the variables are like this. That's important. So once you have a one jet, a derivative of an element of T star n TQ, and you consider the class, it goes to the derivative of the quotient of the section or the map plus something else. This bracket means the notation for the elements of the adjoint bundle, and then you have the connection here applied to the differential. Okay, whatever. So there are two elements. One is the reduced variable, and the important thing is that there is another variable here, right? So the new configuration bundle of reduction has T star n Ts, which is like a jet bundle, but T star n, the adjoint bundle. So there are more variables. It's not a standard variational calculus, the reduced space. So how's reduction? So reduction now is composed by two equations because we have these two variables. Let me go back. So we have this times this and this times this. The first one is a jet bundle, and the other one is the jet bundle of the reduced space sigma, and the other one is, there are new equations, new variables. So we have new equations. So with respect to the variational, the part which is a Lagrange, a tangent part, a jet space, so we have the standard Euler-Lagrange equations, even though there is an extra term here, depending on the curvature of the connection. If you are a good boy or good girl and you consider a flat connection, this part just 0. But if the connection is not trivial, and that happens many times, if the problem requires a special connection, then you have some mysterious forces, like D'Alembert principle, coming from a geometric definition of the connection. This is the first part. But I'm not interested in this equation. Actually, the important one is the second one for my presentation. This one is an equation involving the second variable, right? And this is called Euler-Poincaré. And Euler-Poincaré equations is found in the rigid body equations, are Euler-Poincaré equations, or the Euler fluids, for example, I don't know, so many presentations in these days using fluids with the Euler equations. This is one of these equations, by the way. It's the second one with the proper choice of phase spaces. So this is going to be my first important object, this second equation. The first one is like Euler-Lagrange plus some forces, because there are some forces. But this second one is going to be the conserved quantity. How is a conserved quantity? Okay, so we have the first reduction, and then the philosophy goes to the second part. We have conservation laws. I don't know. There are so many ways of writing down Nether theorem. Probably if Miss Nether, if she enters the room and see the way I'm writing his magnificent theorem, he could complain about this horrible way. But I mean, this is the one I like. So there is like the derivative, and then you plug it with respect to any element of the Lie algebra, the representation on Q, then you contract it by a volume form along a solution, and then this n-1 form is closed. These are the elements, right? So this, the L was a function, so the derivative is like a section of the dual bundle, and then I plug it with an element of the Lie algebra represented on TQ, and then it's a vector field. I contract it with a volume form, and then I compute the differential. I don't know. Probably this other one is closer to classical formulation. I forget this volume form, so remember that this construction is a vector field. So if you stop considering more elements and you forget this volume form, that vector field, that section of Tn, is the vector field, and you can consider divergence. It's a divergence equal to 0, which is like the classical way in physics for conservation laws, right? And we can define like a multi-momentum or a momentum, which is a function sending elements of the jet to Tn. Oh, there is a typo here. This is star, right? So this is a standard momentum, but with Tn, because there are more variables, right? And the definition is like this. When you couple this mu with the an element of the Lie algebra is the element we had before. Okay. So once we have reduction on this, the philosophy, I told you that the presentation was going to be very simple. We have this theorem. So we read the theorem carefully, and we see what's going on here. We have a manifold, and we have a principal bundle, endowed with a principal connection, and then we have a G-invariant Lagrangian here. So there is a reduced Lagrangian. I'm inventing now the sentence because it's not here. But okay, I continue now. The momentum map, mu, the one I defined before, and there is a star here missing, sorry again. If there are star missings everywhere, I'm so sorry. Okay, so this map, if the Lagrangian is invariant, this map is equivariant. Invariant and equivariant is a word sometimes confuses me. I mean, it's the same. The thing is that if the group acts here, the group is going to act here, and the map is consistent with respect to these two actions. That's equivariance, right? So once you have equivariance, you can define a new function in the quotient. So you consider the quotient of this, and then we know that the quotient of this jet is this, using this connection, the one I put before. And you see, the jet times something else, right? And then the quotient of this other guy, I mean, you need some computations, you have the adjoint bundle again, with the star, so sorry, right? So be careful, because this new reduced momentum map is a vector field taking values in a vector bundle. So it's not a standard vector field, it's not a nice object. for example, you cannot consider the divergence of a vector field taking values in a vector bundle. You need a connection, for example. So this object is more complicated, but it's reduced. So that nether conservation law projects to what I said before, the divergence of this vector field with respect to a connection. You need a connection to compute the divergence of a vector field. This one takes value here, vector field, with taking values in a vector bundle. So you need a connection for these objects, right? So this one projects to this. That's up to here. This one projects to here. Okay, you make the computation, that makes sense. But the thing is that this projects to this. I mean, sorry, this equals this, which is the second equation, right? So the second equation is nether theorem. And sometimes it surprises me quite a bit that when you read reduction papers and you have the second equation, they never say that. The authors, sometimes they don't say, many times, most of times, that's actually nether theorem. And actually I think that nether deserves the quotation. So the philosophy is as follows. If you have one map, and if you want to see if it's critical, so you compute the Euler-Lagrange equations, and that's equivalent to the new Euler-Lagrange equations of the reduced Lagrangian applied to the reduced section. Instead of 0 here, we have some force defined by the curvature. You have to impose nether theorem, and something else that I haven't mentioned, that if you are in field theories, these equivalence, at least locally, because there are some topological constraints, deserves or requires some additional equation, which is a compatibility equation, because this is a PDE, and a PDE may define inconsistencies, and you have to impose a compatibility condition of geometric nature. I'm not going to enter into these details. But we have this. And the bridge, the philosophical bridge, is that nether theorem is a part, is not a consequence, it's a part of this equation. So this equation is smaller, but the price you have to pay is that you have to impose this condition, which is first linear, by the way. And it's connected. This philosophy is important if you, for example, you perform reduction by stages. That is, the group of symmetry is like divided in subgroups. So each of the subgroups can be used for reduction. And once you have reduction, you can apply again and again and again. That's very common in many physical systems. So every time you perform reduction, the Euler-Lagrange part becomes smaller, and you put more nether theorems. You put just the nether theorem for each of the groups, and that's equivalence. That's equivalent. It's nice, I like it. So I'm going to finish. Okay, you can use it also for gauge symmetries, and actually that's a work in progress with my student Alvaro, who's there. You can apply also this for gauge symmetries, electromagnetism, Young-Mills. In that case, the symmetries is not defined by a group, but by a Lie group bundle. So things are much more sophisticated, but the situation is the same. The reduction induces two parts of equations, and one of them is nether theorem. You again have the same result. So I just played a little bit, because here there are many talks in this conference about image evolution and computer and geometric computer science applied to medical settings. So I just played a little bit with this. I obtained some equations, and there is a typo again. But okay, just to finish, I'm just going to say some few words about, for example, a setting where you can find this. I mean, if you consider a Q as the space of embeddings, that is closed curves, parametrized closed curves on the plane, and you consider R2 as N, you are playing like or your objects are like curves on the plane parametrized by two parameters. One is time, so you are evolving the curve with respect to time. And another parameter is because, for example, you have a family of curves. If you have a tomographic image of your brain with different slices, so the parameter of the different slices is one parameter, and the time evolution of each of them is the other parameter. So these are the two parameters here, for example. And generally, the geometric problems are if S in one invariant. So you can consider the action and the quotient. This quotient is the shapes. This is called the space of shapes. There is a canonical connection, by the way. It's just considering once you have a tangent vector, which is like a vector field along the curve, you consider the perpendicular and vertical part with respect to the curve itself. That's a natural connection. So you can perform reduction. So you have like thousands of possible Lagrangians. I've just taken two of them, which are awful. I mean, forget the formulas, because actually this morning there were like 2 talks talking about possible Lagrangians, by the way. Okay, you can take any of them here. They are give Lagrangian, otherwise they don't make sense. And I considered one of them. This is the Frenet curvature here. This is one of the Lagrangians. This is another one, considering this is a Sobolev Lagrangian, considering derivatives with respect to the R parameter. The Lagrangian is divided into 2 parts. Actually, this is because I'm using that connection to split the the normal and tangent parts of the derivatives. And I don't know, I just consider the Neyer conservation law, and there is a typo, but you get something like this. I don't know. With the second case, by the way, with this one, with the Lagrangian L equals L1 and L2, the so-called Sobolev Lagrangian, you have one equation like this. I don't know. That's a conservation law, actually, with respect to the group of diffeomorphisms. And that's also an equation, which is the philosophy I wanted to express now. And I think that's enough. Thank you very much.